So Newton's third law of motion can be restated from the formal definition as for every action there is an equal and opposite reaction. And so this holds true even for extreme examples. For example, if you're driving down the road and you make contact with an insect that's flying around, the bug splatters on the windshield of your car, and so the question is the force experienced by the bug greater than, less than, or equal to the force experienced by your car? And as you can infer from the topic that we're covering here, the answer is it's equal to. Now, the force that the car is experiencing is the same as the force that the bug is experiencing. Well, how can that be when the car is remaining intact versus the bug, which is going to get splattered? Well, if we take each of these and set them equal to, instead of force equals force, but mass of the car times the acceleration of the car equals the mass of the bug times the acceleration of the bug. If we set those equal to each other, now let's say the car is something around 2,500 kilograms, not an unreasonable estimate, and let's say its acceleration is something low, like even on the order of 0.1 meters per second squared, something very low. If the bug weighs a gram, 0.001 grams, it doesn't take much to see that the acceleration of our bug is going to be something that's going to be significant. So as a result of this extreme acceleration that this bug is going to experience, it's going to get destroyed. And this would be true for humans as well. We will study this in a later unit, in our bioengineering unit, but even on the order of something over 30 Gs for any meaningful amount of time, even with no impact, is enough to kill a human. Now we're having a collision on top of this acceleration change for the bug. You can see why it doesn't go well for our insect friend. In the second example, we're looking at a space transport that's trying to overcome gravity in order to be able to take off into space. And so we see that the weight of the space transport is that 4.4 million pound force. Remember, weight is a force. And then the liftoff thrust is that 6.78 million pound force. And so we want to know what's the unbalanced force that the shuttle has to overcome, needs to have in order to overcome gravity. And so we can just quantify this as the unbalanced force is equal to the force of the thrust minus the force of the weight. And so we're just going to subtract these two quantities. The force thrust, 6.78 times 10 to the 6th pound force, minus our 4.40 times 10 to the 6th pound force. And so we get this unbalanced force in this circumstance is 2.38 times 10 to the 6th. Now, that's not too challenging, but it is related to a topic that vexed scientists for quite a while, which was whether or not space travel and movement in space would be possible by rockets, rocket-powered space shuttles and objects would be possible at all. And the concern was that there would be no reaction force to the action. So if you have the rocket expelling gas out of the bottom, what is it pushing off of? And so the thought was, on Earth, the rocket can take off because it's pushing off of the Earth, but instead in space you don't have any ground or anything like that to push off of, so would it be possible at all? And the end result was theorized that indeed it would be possible, because the action-reaction force would be the rocket expelling the gas and then the gas pushing back on the rocket. And so there's your action-reaction pair, which allows that movement. If there was no reaction force, then you would just have the expulsion of the gas going one way without any commensurate reaction force that would allow the rocket to fly forward. So it was based on Newton's third law that it was determined that rockets would indeed be able to propel themselves through space. So our last example has a little bit more going on. So in this case, we have a bullet that's being fired from a rifle. We can see the masses given to us there. And we're told that the initial velocity of the bullet from the rifle is 1,000 meters per second. And we're also told the length of the barrel of the rifle, which is important because to determine the acceleration of the rifle, we're going to use this equation right here, 0.5 times v squared divided by the barrel length. And so what we want to try to find is what's the recoil that we experience from the acceleration of the rifle, because when the bullet is expelled from the rifle, it is pushing back on the rifle, which then pushes onto your shoulder. So we want to see what is the acceleration of the rifle, and therefore the impact eventually that's going to be experienced in the shoulder. So to start off with, let's get that force that's on the bullet. And so that's going to be mass times acceleration, but we have a mass of 15 grams, so that'll be 0.015 kilograms. Need to make sure that we use our kilograms there. And then for the acceleration of the rifle, or of the bullet I should say, it's going to be 0.5, and so that's not contributing to our significant figures, just to clarify. So we got 0.5 times 1,000 meters per second, and then it's that quantity squared, and then that's all over the barrel length of 60 centimeters, which I'll immediately convert to 0.600 meters. I think I missed a 0 on my kilograms there. So we can see that we've got a mix of 3 and 4 significant figures, so we're eventually going to round off our answer to 3 sig figs. And so if we push buttons on our calculator, we'll round off to 3 significant figures, so we're going to end up with an answer of 12,500. Again, that was acceleration or force that we were solving for, so 12,500 newtons. So that's the force that's being applied to the bullet. So what's happening with the rifle? Well, for the rifle, it's going to be that exact same 12,500 newtons. For each action, there's an equal and opposite reaction. So then I'm going to set that equal to the mass of the rifle, 5.0 kilograms, and then times the acceleration of the rifle, which is what we're eventually solving for here. So I can now take this, just divide both sides by 5, and I get the acceleration of the rifle is going to be a healthy 2,500 meters per second squared. And now we have to think forward, even though we're not asked to solve that here, what's going to be going on at our shoulder? Well, it's going to be the exact same force that's going to be distributed to our shoulder by the back of the rifle. And so then we would set the force here equal to our mass, and then we would see what the acceleration is that we would be experiencing as a result.